Profesor Ida Bagus Rahmadi Supancana, Dr. Bambang Sumarwoto, Profesor Sugihiro Takahashi as our keynote speaker. Ladies and gentlemen, the theme of the ISAST 2022 is Science, Technology, Policy, and Industry Development on the Aeronautic and Space, which is relevant to our situation nowadays. Our keynote speaker. As we know that massive change have taken place, new trend emerged in various aspects of life, not limited but in the field of social, informatics, and and also, of course, in the field of aeronautic and space. This featured researchers around the world to innovate to solve various problems. Therefore, the demand of the field of research achievement rise. Of course, also then the question of the global progressive research. The renowned advance in the field of research and technology is vital of the national achievement. One of which is in the field of aeronautic and space. Hence, ISAST 2022 established to accommodate the meeting of world-class researchers to conduct collaboration research in the area of science, technology, policy, industry development on aeronautic and space. We strongly encourage you to take as much as benefit as you can from this ISAST 2022 and wish you a fruitful conference. Thank you very much. We strongly encourage you to take as much as benefit as you can from.
Thank you, Mr. Faro Haji. Excellencies, participants, ladies and gentlemen, now we are going to listen a welcome speech by the Chairman Research of Organization for Aeronautics and Space. Please welcome Dr. Robertus Heru Triharjanto.
Good morning, ladies and gentlemen, our participant of International Seminar of Aeronautic Aerospace Science and Technology, number 9 in 2022. First of all, I would like to say Assalamualaikum warahmatullahi wabarakatuh. God bless to you all. Om Swastiastu, Namo Buddhaya, Salam Kebajikan. I would like firstly to thank the ISAST committee for conducting this activity. This ISAST number 8 we conducted on 2022, and then because of the planning during the pandemic era doesn't allow us to have it in 2021, the ISAST number 9 was can only be done in 2022 or today. And the secondly, I would like also to thank the chairman of BRIN, Dr. Laksana Trihandoko, for supporting the event and also I would like to say welcome and thank you for our colleague that become a keynote speaker, Takahashi Sensei, who is my long friend, and also Dr. Bambang from NLR and Shiokawa Sensei from Nagoya University. I would like to express my sincere thanks to you to participate in our international seminar. So, ladies and gentlemen, this ISAST 2022 is the first time that to be held after the integration of LAPAN into National Research and Innovation Agency, or BRIN. So, with the new format, the Research Organization of Aeronautic and Space is only concentrating on academic work, performing research and development. Meanwhile, the role of space agencies previously held by LAPAN is now done by BRIN. Among others, the remote sensing data services is done by BRIN, and only the role of Research Organization of Aeronautic and Space is only in supporting the developing the development of the methods to extract the information from such data. And also BRIN as a space agency will represent Indonesia in international space forum, such as conducting or hosting the UNESCAP Ministerial Conference number 4 last month, and also conducting the Space Economic Leaders Meeting, who was one of the side event from G20 Indonesian presidency. Ladies and gentlemen, scientific publication in one of the necessary element in building research ecosystem. That is why the Research Organization of Aeronautics and Space is sponsoring ISAST, and also at the moment is sponsoring the new journal. It is called Indonesian Journal of Aerospace. This new journal is uniting the Jurnal Teknologi Dirgantara, Jurnal Sains Dirgantara, and Jurnal Kajian Kebijakan Penerbangan dan Antariksa, previously sponsored by LAPAN. Meanwhile, the remote sensing journals previously managed by LAPAN as well, both international and national, will be managed by the professional association. In this case is Remote Sensing Society or MAPIN and Indonesian Geography Association or IGI. Ladies and gentlemen, another aspect in building national aerospace research ecosystem is also developing professional communities, association. So in addition to BRIN's open infrastructure policy, the future academic seminar and the journal management is expected to be done by professional association. At the moment, we do not have yet professional association in the field of elements of aerospace research, such as aerodynamics, astrodynamics, astrophysics, flight dynamics, and aerospace propulsion. So in the future, we would call on all of you, the academic communities in aerospace, to form such an association, and Research Organization of Aeronautics and Space will sponsor in the form of hosting the secretariat of the association. Ladies and gentlemen, it is quite unfortunate that in today's seminar, we are unable to see each other face to face, because this seminar, as in many government events, was planned a year before. So we were planning this seminar at the time when the pandemic is still at the peak. So we are hoping that the next year's International Seminar of Aerospace Science and Technology can be conducted in face-to-face format. So we can even further build the networking between academics. And without further ado, I would like to wish you all a successful seminar today. And with closing, I would like to say Assalamualaikum warahmatullahi wabarakatuh. God bless to you all. Om Santi, Santi, Santi Om. Thank you.
Thank you, Dr. Robertus Heru Triharjanto. So, Excellencies participants, ladies and gentlemen, let us follow the opening remarks, which will be delivered by the Chairman of National Research and Innovation Agency. We will replay the BRIN's conference opening remarks by Dr. Laksana Trihandoko, which was delivered on the 21st of November 2022. Marks by Dr. Laksana Trihandoko.
Thank you very much.
Which was delivered
Everyone,
on the 21st
very
of
good
November
morning.
2022.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera, salam sehat untuk semuanya. Salam, Om Swastiastu, Namo Buddhaya, salam kebajikan. To the Honorable, our keynote speakers, everyone, one keynote speaker from WIPRO, Secretariat China Office, and also the Vice President of the ITRI China, Dr. Paul A. Burrows, and the Honorable Acting Deputy, our Deputy Chairman for Human Resources, Science and Technology, actually who is leading this event and has facilitated hosting the conference, and all of distinguished experts and speakers and also participants actually who is leading. So first of all, I would like to hosting the conference, and all of first of all, it is a great honor for me to be here to join this international conferences, consisting of many international conferences, covering various research fields. And it is a great pleasure for me to meet you all, even virtually, consisting of many international conferences. Ladies and gentlemen, the participants, the scientific publications is undoubtedly very, very important for all of us, the academia, either from universities and also from research institutions like BRIN. And it is also essential to develop a new knowledge through the scientific publication. And conferences, on the other hand, is one of our tool, our instruments to make interactions, to know each other, to discuss many interesting findings, interesting invention, innovations coming from another researchers and academia across the globe. So, and actually, this is the basic of our research activity conducted by researchers wherever you are. So now, after the establishment of BRIN, the National Research and Innovation Agency, we have already integrated all of governmental research institutions across this country, Indonesia, and of course that also means we carry over all of the related activities, including hosting some conferences, also managing some research journals, and also some workshops, and so on and so forth. And considering to how we could improve the efficiency and the productivity of our research activities. At the end of the day, I would like to inform you that we have decided to integrate all of the scientific conferences we organized previously by the former research institutions into a single series of scientific conferences, international conferences. We do expect that through this initiative, we can invite, we can attract more external researchers to join our conferences, so we can realize and also we can achieve better environment, not only for our researchers but also for researchers in Indonesia in general. So hopefully, we could continue organizing this series of international conferences, starting from this year, and hopefully we can continue also next year and many years to come. But more importantly, I personally already requested to our researchers to consider how to integrate more the existing international conference request so we can make it more attractive and also much more, on the other hand, much more efficient, how to integrate all of us in the future more. So I do believe in the how to integrate, but we do still we have to more improve the existing improving organizing, make it more attractive, which and also much more, on the other hand, much more efficient. How we cannot just have all of us many in the future more conferences. I believe in the research fields, but we have to somehow, for example, do still we have to consider to improve the existing. To exchange ideas, to have the interactions among researchers with different backgrounds, with different disciplines, and so on and so forth. So I think this is very important for us to make continuous improvement, in some sense, to exchange in order to ideas, our activities, to have the interactions among and not only with different backgrounds, with different disciplines in and so on and so forth. In the case of, so I think this is very important for us to research area, which might be to make interesting for continuous improvement, in some sense, to exchange in order to ideas, I think activities have the interactions among and not only with different backgrounds, with different disciplines in and so on. In the case of, so I think this is very important for us to enjoyable research area, which might be to make interesting for continuous improvement, in to exchange in order to ideas, I think activities have the interaction among and not only with different backgrounds, with different disciplines in and so on. In the case of, so I think it is very important for us to enjoyable research area, which to make interesting for continuous improvement, to exchange in order to ideas, I think activities have the interaction among and not only with different backgrounds, with different disciplines. In the case of, so I think it is very important for us to make interesting for continuous improvement, to exchange in order to ideas, I think activities have the interaction among and not only with different backgrounds, with different disciplines. So I think it is very important for us to
Ladies and gentlemen, we apologize for some trouble here. So anyway, we are now continuing our event to the next agenda, that is keynote session. This keynote session will be moderated by Mrs. Lilis Mariani. In this session, there will be 3 keynote speakers as follows. First one is Professor Yukihiro Takahashi from Department of Earth and Planetary Sciences, Cosmos Sciences, Hokkaido University. Second one is Dr. Bambang Sumarwoto, the senior scientist of Royal Netherlands Aerospace Center. And the third one is Professor Kazuo Shiokawa from Center for International Collaborative Research, Institute for Space Earth Environmental Research of Nagoya University. We invite Mrs. Lilis Mariani to lead this session. Without any further ado, please welcome Mrs. Lilis Mariani. I'm sorry, Mrs. Lilis, we cannot hear your voice. I'm sorry, Mrs. Lilis. Lilis posisi di mana? So seems like we cannot still hear your voice. Okay, ladies and gentlemen, maybe there are some troubles there. So please wait for Mrs. Lilis to get ready.
Ini nyalain aku. Nyalain suara-suara. Hello, can you hear me now?
Oh, okay, yes.
Okay, then I will have to start from the top again, okay? I'm sorry for the connection because I don't know why the sound is not coming out. Okay. And okay, Assalamualaikum warahmatullahi wabarakatuh. May peace be upon you. Good morning and good afternoon. And once again, I would like to extend my welcome and thanks to the chairman of Okay, sticky. Okay, now it's working now. I'm sorry everybody for some misconnection. Okay, I would like to extend my thank you and welcome to all the participants and distinguished guests, especially the keynote speakers and also the head of Aeronautics Research Organization for Aeronautics and Space. And my name is Lilis Mariani, and it is a great pleasure to be your moderator for the 2022 International Seminar on Aerospace Science and Technology. Ladies and gentlemen, as we know that the aerospace science and technology has rapidly developed for the last centuries, and its application has touched many aspects in our lives. It allows us to do the space exploration, transportation, remote sensing, and climate disaster mitigation, and many things. So in today's seminar, we are going to take a closer look, especially from the three keynote speakers that are going to present today. Professor Takahashi, and then also Dr. Bang and Professor Shiokawa. Thank you for taking your time to join us today. And before we start, I would like to tell you how this seminar will run. We are going to listen for three keynote speakers. Each will present for about 40 minutes. And then after that, we are going to have a question and answer session for 30 minutes. So the participant can give your questions in the chat box and we will read your questions. I hope you will be taking these opportunities to ask from the special expert in their fields. Okay, now, ladies and gentlemen, let's move on to our first keynote speakers, Professor Yukihiro Takahashi. First, I would like to read his bio. Okay. Professor Yukihiro Takahashi started working at Hokkaido in 2009, and he's noticed that the sophisticated microsatellite equipped with the advanced sensors such as liquid crystal filter telescope are very useful for forestry, agricultural, and fishery, and so on. Now, Professor Yukihiro Takahashi has been participating in many joint projects with other professors in such areas, And his research mainly focuses on natural sciences, space, planetary science, environmental science, agricultural science, and many things. Okay, let's give, without further ado, to welcome Professor Yukihiro Takahashi. The screen is yours, sir. Thank you. Good morning, Sensei. Yes. Your voice is not, we cannot hear you. I think it's still in the, yes, please try.
Okay, thank you very much.
Okay, we can
I'm
hear.
Hiro Takahashi from Hokkaido University. Thank you very much for inviting me to this exciting meeting. So, can I share my screen?
Yes, please.
Please give permission.
The,
Yes.
oh, okay.
Please
Your
give.
voice is not, we cannot hear you. I think it's still in the, yes.
Hello, hello, can you hear me? Thank you very much.
Okay, we can
Hello,
hear.
Hiro Takahashi from
I can hear you
Hokkaido
fine
University. Thank you very
here,
much for
but I'm not quite sure the other.
exciting meeting. Can I share screen? Can I share my screen?
Yes, please.
Please give permission.
The,
Yes.
oh, okay.
Please
Your
give.
voice is not, we cannot hear you. I think it's still in the, yes.
Hello, hello, can you hear me? Thank you very much.
Okay, we can
Hello,
hear.
Hiro Takahashi from
I can hear you
Hokkaido
fine
University. Thank you
here,
very much for
but I'm not quite sure the other.
exciting meeting. Can I share screen? Can I share my screen?
Yes, please.
Please give permission.
Kayaknya telingannya. Yes, Professor Yukihiro Takahashi, you can give your presentation now.
Yes.
I think there is a problem in the internet connection, so your voice it's kind of delay, a little bit delay. So, but we will try. Okay.
Can you hear me?
Yes, sure.
Okay, thank you very much. So I'm Yukihiro Takahashi from Hokkaido University. It's my great pleasure to present the my works related to the microsatellite today. So I believe that the microsatellite has a great potential for contributing to next generation Earth monitoring. So this picture was taken by astronauts in international space stations. So this is the first Philippine satellite developed in our university. So the dimension is 55 by 35 centimeters, like as the Indonesian microsatellites. The body is very small, but the performance is even better than big ones, big satellites in some aspects. I want to introduce the possibility of this kind of instrument to contribute to the geosciences and Earth monitoring today. So there are so many global issues to be solved. So for example, the food problem related to the agriculture and drought and fisheries and the big natural disasters such as volcano eruptions, tsunami, and flood caused by the torrential rainfall or typhoons, and which will cause the landslides as well. And also the forest fire is a very big issue, especially for Indonesia, because the forest fire emits so much amount of carbon dioxide. It's almost equivalent to the total artificial activities. So therefore, management of forest fire is very, very important subject for the human beings. But the problem is that the two monitoring. Somebody's mic on. Still somebody's mic on. Okay, so we need to monitor the very broad area in a very short period to adopt the actions for mitigating the effect of disasters or climate changes. So we have a lot of issues again. So, but we need to find the very serious area and serious phenomena in a very short period. But so far, it's not easy. So of course, the satellite, there are already so many satellites in space, but unfortunately, satellite monitoring is very strong, but there are very big two issues to be solved. One is the long revisiting intervals. For example, the Landsat 8, very famous satellite launched by US, can visit a certain place only once at 16 days. It's too long for the application of disaster monitoring or agricultural purposes. And another part is the low reliability of obtained information by satellite images. So today I want to concentrate not the communications, but only for the remote sensing of the Earth. So the reliability means if we want to know the condition of agricultural farm, we want to know the growth stage of the crops or the expected amount of crops or disease in the field. But it's not sufficient for the most of the conventional existing satellite to do this. I will explain the reasons afterwards. And also the satellite is so expensive that we cannot increase the number of the satellite easily. So therefore, in most cases, the revisiting period is too long. But our advanced microsatellite, of course, our includes Japan and Indonesia. So we'll solve these issues in the near future using the microsatellite. So this is one of the example of our satellite named Rising 2. So to monitor the lightning activities from space. This satellite has a dimension of 50 centimeter, 50 centimeter, and 50 centimeter, the complete cubic, and 50 kilogram. So, but this small body has different type of sensors, and the total CMOS and the CCD is about 8 sensors. So therefore, one small body can capture various kinds of information at different wavelengths and different resolution and coverage of the land. So we, Hokkaido University and Tohoku University, have been working together on this development, not only inside Japan, but also with partners in the world, in Asia. So this is the kind of example of the satellite launch. So the upper left shows the condition of the inside the rocket, top of the rocket. So we can see the GOSAT, a big satellite developed by the JAXA, Space Agency of Japan, and the small satellites are surrounding the big satellites. So the right bottom shows the pictures taken by this big GOSAT satellite just after detaching from the rocket body. So we can see the small satellites still on board the rocket body, but these are detached. These were detached safely in a short time later. So we captured very nice images from this satellite successfully. So this is our Hokkaido Tohoku University's first microsatellite. So since then, we launched 6 satellites in total, and all these satellites were successful. So the microsatellite here, we define the 50 kilogram satellite, but sometimes smaller than this. So the smallest satellite in the world is the 1 kilogram satellite. We call it CubeSat, and 3 kilogram, 6 cube, 6 kilogram, around that. And on the other hand, larger satellite. Larger means small to middle to big satellite. So the small satellite means over 200 or 300 kilogram generally. So this larger satellite takes more than 10 years from idea to launch, mostly developed in a space agency, the big space agency in the world, NASA, JAXA, or ESA, or somewhere. And it costs about few hundred millions of dollars. So it's very expensive. So, but on the other hand, our satellite costs about a few million US dollars, and we can fabricate it in a year or even shorter. So sometimes we completed the fabrication in half a year. So therefore, we can apply the latest technologies to these microsatellites. So LAPAN, they succeeded in launching the 3 satellites already. So it's very excellent work, I think. So, and if we can work together with Japan, then we can install some of the cutting edge sensors to obtain more reliable information of the agriculture or ocean area or the all air information in the world. So, but I don't want to say the microsatellite is almighty. It's similar to the relationship between the personal computer and the supercomputer. We need a supercomputer to predict the climate changes. On the other hand, our daily life are supported by the personal computers. So we need to make use of these kinds of instruments according to the purpose. This is a point. It's not competing, it's a collaboration. So these 10 or 20 years, the smaller satellite increases these numbers. So increasing these numbers. So after 2014, the more than 100 satellites, micro or nano satellites are launched in a year. So now more than 50%, the micro satellites occupied all the satellites launched in a year. So this is not only for the experiment or education or exercise, but it's almost almost became the social implementation method. So the first problem, the low revisiting intervals of the satellite, how to overcome these issues. So one of the ways is to increase the satellite. Because of the conventional satellite scans only the narrow swath just below the satellite. So the 200 kilometers in Landsat case. And the other satellites as well, not so different. So therefore, we need to scan so many times to know the whole area of the Earth. So one of the solutions is to increase the number of the satellites. So, but we take another way. So this is the multi-point imaging by rapid target pointing method. This is the similar way of the LAPAN. So we can manipulate the attitude of the satellite to point the specific area where we want to see. So the camera has a high resolution, but we don't want to monitor the whole area, but the specific area where something happens, such as the forest fires or tsunami or volcano eruptions. By this method, we can detect the detail and precise information only with a small satellite efficiently. So but unfortunately, this kind of target pointing is not popular in the world. So most of the micro nano satellites are just tracing the same method of the big ones. So but I think the smaller satellite is not just a copy of the big satellite, but the new method, the new innovative method to make the next generation space utilization. So our satellite can watch any place from place to changing the target in 1 or 2 minutes, and the pointing accuracy is 0.05 degrees. This is even better than big satellites already. One of the application of a microsatellite is the new method of extreme weather monitoring. So this is our experimental project in the Philippines. So we distribute the ground stations to monitor the weather, extreme weather, the torrential rainfall or typhoons, and also the lightning sensors on the ground. We can detect the very dangerous thunderstorms, the lightning occurrence, by measuring the radio waves emitted from the lightning stroke. Then this information can be summarized in a center, and we can determine the most dangerous thunderstorm location. And right after this detection of the thunderstorms, we can ask our microsatellite to watch this specific area in detail. So by this method, we can get very detailed information and precise information of thunderstorm development, which cannot be measured even with the latest radar systems. I will show this example. So our on-demand target pointing is the new method for the space development in the world. Of course, there are some satellites which can change the field of the camera according to the situation. If the very, very big disasters, for example, magnitude 9 earthquakes happens, every satellite in the world can monitor the specific area. But every day we have the thunderstorms, and every day we have the serious forest fires. In that case, we cannot use the bigger satellite by manipulating the attitude. But for the micro satellite, it's quite easy. So now we don't need to use the big monitors to operate the satellite, but also with very tiny personal computers. So this picture shows the actual situation of the satellite monitoring. So satellite monitoring and operating. So this person is our colleagues in Hokkaido University. He's now operating the satellite, watching the health condition of the satellite and changing the attitude. So this kind of active operation can be possible also by LAPAN group, I know. So it's very, very excellent method to decrease the cost of the operation and earn and get only the effective information. So we don't need to monitor everywhere at the same time, but we need to concentrate on the very specific area. So, and also by using the target pointing, we can make the multiple exposures from slightly different angles to make the 3D of the clouds. This 3D estimation of the cloud structure is a very important issue to predict the near future precipitations. Okay, so this is one example made by our measurement from probably 5 or 10 pictures taken from the different angles. This is the cloud top features estimated by our microsatellite measurement. So we compare this one with the Himawari 8 measurement. Himawari 8 cannot make the 3D measurement, but Himawari 8 is measuring the temperature by thermographic camera. So therefore, we can estimate the height of the cloud top, assuming the temperature of the cloud particle is the same as the ambient atmosphere. So then right side shows the Himawari 8 height distribution of the cloud, same area, and left side is ours. So you can see that these two pictures shows the same tendency, but the resolution, the ground resolution, spatial resolution is 20 times better than Himawari 8. So this very cheap satellite, probably the 1 or 2% of the Himawari 8 achieved the very precise measurement of the cloud structures. This was appeared already on the scientific journal papers. And this is another product of our 10 seconds measurement of the cloud. You can see very precise 3D model was made only by the microsatellite measurement. So therefore, if we can apply this technique to the thunderstorm measurement, we can monitor the development, the stage of the thunderstorms more precisely. And from the estimation of the cloud volume, we could know the future precipitations. And also another subject is the typhoons. A typhoon seldom hit the Indonesia, but in Japan or other tropical areas, the hurricane, cyclone, and typhoon are the very, very big issues, which causes a lot of sacrifice due to the precipitation, flood, and high tide. So, but unfortunately, so far, it's very difficult to know the center pressure. So because the typhoon are developing mostly in ocean area. So we have a very limited number of the ground stations. So therefore, generally, we need to make use of the Himawari data to take the visible wavelengths and thermal infrared images and compare with the former patterns. And matching these patterns, we need to estimate the minimum pressure at the center. But apparently, it's not a good way to know the precise pressure or the wind velocity. So here we consider the Typhoon I is the main, the very important subject to observe, because if the typhoon intensity is very strong, then the eye became very small but very deep. Even we can see the ocean from the space. So, and on the other hand, the typhoon was weakened. Then the eye became larger in diameter, but it's very dim, and we cannot see the ocean from above. So if we could know the very precise feature of the cloud in the typhoon center, then we can estimate the precise intensity of the typhoons, the minimum pressure or maximum wind velocity. So to do this, we could make the 3D monitoring using the microsatellite. So this is the case of typhoon number 9, 2020. This picture was taken by the fisheye camera, a low resolution camera. And this typhoon already over the maximum. So it's now diminishing, but still we can see the center of the typhoon clearly. So this picture was taken by Diwata 2, the second microsatellite launched by the Philippines. So we are working together with the Philippine guys and ask them to capture the center of the typhoons by manipulating the attitude of the satellite. So this is the center image, the telescopic image using the different camera on board the same satellite. So that we can see the very fine structures of the center of these typhoons. So the resolution is 40 times better than Himawari satellite. So we capture this image slightly different angles continuously like this. So these pictures may be at the 10 or 20 pictures taken from slightly different angles, but these pictures are enough to reproduce 3D structure of the clouds. So this is the result of the 3D analysis. It's not special. Just put this in the pictures to the very ordinary 3D softwares. So we can see the center region has very deep structures rather than the ambient areas. And we can see the spiral clouds as well. So in the future, we want to estimate the pressure, the center pressure using these structures. This must be much physically important than just comparing the patterns of the cloud distributions by the former the experience and Himawari or the other usual conventional satellite images. So this is another typhoons. It's this year, number 11. Fortunately, the satellite passed over the center of the typhoons. So this is again the low resolution data. The height of the camera, height of the satellite is only 600 kilometers. Therefore, the horizon is very close. It's not half of the Earth, but only 3,000 kilometers away from the center to the horizon. So we can see the very clear spiral structures originated by the typhoon activities. And we can see very deep black at the center of the typhoons. We capture this image, the telescopic image, focusing on these center structures, because as I said, the monitoring the center cloud structure may useful to estimate the intensity of the low pressure. So this is the consecutive image of the center using the telescopic camera. So the resolution is probably 40 times better than Himawari, and this diameter of this hole, the typhoon eye, is about 10 kilometers or less. So this is the every 24 seconds the images taken by our satellite, Diwata 2. So we can see the internal structure of eye wall cloud very precisely. This must be the world first results of a typhoon measurement, which cannot be done even with the other latest and expensive satellite. So probably the LAPAN satellite can make this the similar measurement and 3D reconstruction easily. So therefore, if we work together, then the observing frequency will be improved significantly. So then we can contribute to the prediction of the typhoon activities. So also, we have been developing the thermal infrared camera at the 10 micron range. So we installed at some satellite developed together with other universities in Japan. So right side shows our second satellite, Rising 2 images. So the blue color means the low temperature. Low temperature means high altitude cloud top. So this is the typhoon image, so that we see the development of the typhoons. But again, as I said, only the temperature measurement is not sufficient to monitor the exact height of the typhoon clouds. So therefore, we need to combine these kinds of thermal infrared camera data with 3D reconstruction images taken by the visible wavelength range. The left side shows the volcano eruption signatures. So this was happened in 2014. The one volcano, not so huge, but very dangerous, the Ontake volcano eruption happened. So the more than 30 persons were killed due to these eruptions. So we can see the bright area in 10 micron range circled by red lines here. So we see very high temperature around the volcanoes. So this is just after the eruption, but it's a first image taken by the satellite for this eruption event. So now we developed another thermal infrared camera in Hokkaido University, and I brought this to LAPAN, the BBPT and LAPAN. Now the UA-BRIN. So as a part one of the scientific payloads on board A4 satellite. I hope our infrared camera will work for the detection of the volcano eruptions, cloud temperature, and forest fire detections. So I'm praying the successful launch in the near future of the A4 satellite of the Indonesia. So the other topic is the vegetation monitoring. So nowadays, a lot of satellites are working for the smart agriculture, monitoring the stage of the growth or estimation of the crops or detection of the disease. But most of the agriculture application depending on the NDVI index. That this is the kind of the normalized difference vegetation index. Many people believe in this index, but unfortunately, we found that this index is not sufficient. So this is because the reflection of this is a example of the spectral reflectance of the wheat. So the green line is the healthy one, and others for different diseases. But apparently, this line shows the different features. If we get these lines, it's easy to identify the disease species. But unfortunately, if we have BGR and NIR channels, the information became so small like this. So then only the vegetation index are made of the NIR and R intensity, red intensity. So the information is quite limited. So it's not sufficient. So we tried the application of NDVI in rice field using drones. So this is the research farms. So therefore, the crops is quite ununiform. But unfortunately, the NDVI shows the almost homogeneous and correlation efficiency between the NDVI and the resultant crops has only 0.5. It's not too bad, but it's not sufficient for the farmers. And also, this is a detection of the disease of oil palm. Oil palm is very important industry in Indonesia and Malaysia. And 15% of the vegetation was degraded by the disease. But as you see, the black dots shows the location of the disease trees. But NDVI shows exactly the same as healthy ones. We cannot see we cannot see the disease of the oil palm by NDVI. But how to improve this NDVI? The key keywords is the spectral imaging. So if we can make use of not only BGR and NIR with broadband filters, but we pick up the specific bands by the new spectral camera, then we can derive the reliable information from that. So this is the application of the spectral imaging using the all spectral combinations to make the new index NDSI. So then we found the best combination of two bands to estimate the crop is here the two bands, specific two bands, which shows the more than 0.9 correlation efficiency easily. So therefore, if we choose the best combination of the bands, then we can easily achieve the very useful index. And this is another case. The oil palm disease can be detected if we applied artificial intelligence to calculate to estimate the location of the disease trees. So therefore, the spectral information is very useful, but unfortunately, up to now, it's not common. There are two big reasons. One is the spectral camera is very big, heavy, and expensive. So for example, the satellite-borne camera made by the Japanese government cost about $150 million US only for camera, not the satellite. It's too expensive. So this is a diagram of the camera on board the satellite, on board the satellites in the world. So the left, the horizontal axis shows the number of the bands, and the vertical axis shows the ground resolution. Most of the cameras are concentrating between band 4 and 5, and the resolution is a few meters. But these cameras cannot provide sufficient information for agriculture. At least we need more than 100 bands, but only 3 cameras in space are working for the spectral imaging. Besides our satellite, our cameras are indicated by red circles here. So it's extreme and very useful. So our camera can choose any bands rapidly, mostly in 30 milliseconds changing time. So then the resolution, ground resolution, our best one is the 5 meters. And while the other spectral cameras has only the 20 or 30 meter resolution. And our camera is only 3 kilograms and much cheaper than $1 million US, which can be on board microsatellite. And another problem is the spectral changes due to the lighting and observing angles. So if we observe only a 20-degree difference, at the 20-degree difference causes totally different spectrum. So to overcome this issue, we developed small compact spectrometer to measure all combination of the angles on the ground. So we developed this one. It's very cheap. Generally speaking, the standard spectrometer on the ground costs about $100,000, but ours is only $1 kilo US. So everybody can use it, even the farmers. I asked the farmer to monitor, to take the spectrum from different angles. So then he worked very hard and got the very important information. We put on the top of the automatic gimbal at the top on the 9-meter poles like this. We can cover the up to 50 or 60 meters around the from the pole like this. Based on this information, we can determine the best bands for the measurement by microsatellite. So this is a case of the new Panama disease in the Philippines. So we measure the healthy and the disease leaves on the ground by the spectrometer, and pick up the very important bands, and then ask our satellite to capture this image, not the whole 100 bands, but only 3 or 5 bands. Then we can identify the disease expected area successfully. The red dots means the satellite prediction of the disease, and the yellow ones is the ground truth. The center 3 yellow dots are not accompanied by red dots because of the cloud. If the sky is clear, we can identify the disease from space. This kind of technique can be applied not only to the banana, but also to the other crops as well. So, and the identification of water area is quite easy for a spectral camera, and pollution of the water, the ocean water as well, picking up the best of 4 bands among 590 bands. So this kind of technique can be applied not only to the agriculture, but also to the ecosystem environment monitoring, disaster monitoring, forest and forestry management, mineral resources as well. So now we have been working on the establishment of the community named the Asian Microsatellite Consortium. The Indonesian agency is also the member of this consortium. So the concept is the sharing data, technology, and application, not building the satellite, not just operating the satellite and share the data, but the sharing the machine time of the satellite. This is a final goal of our activities.
2 minutes more, Professor.
Okay, so this is the super constellation under international corporations. If we have only 50 satellites, the Elon Musk says the 10,000 satellites, but we only have needs only 50 satellites, then we can cover whole world like this. So, and we can contribute to the many subjects of the SDGs related to issues. And this is a conclusion. So how to improve the observation frequency and reliability by the satellite? The spectral information is the very key issue to improve the accuracy, and the frequent revisiting period can be achieved by the target pointing. And also liquid crystal can improve the accuracy of the spectral measurement. And in order to achieve the above all, the important is the grand spectral library made by members, not only by Japan, but also with the Indonesian guys and other countries as well. And international cooperation is very important for developing the new methodology of the space utilization. Thank you very much.
Okay, thank you very much, Professor Takahashi. It's very interesting and very comprehensive presentation. Ladies and gentlemen, now we are moving to the second keynote speakers, that is Dr. Bambang Sumarmoto. Please, Dr. Bambang, go ahead. The screen is yours. Is Dr. Bambang here? Okay. We still cannot hear your voice, Dr. Bambang. It's still muted. Hello? Pak Bambang masih suaranya nggak ada. We still cannot hear you. Please unmute.
Okay.
Thank you.
Yes, thank you.
Go ahead, Dr. Bambang. You can.
Yes, can you hear me?
Yes, sure.
And now I'm going to try to share my screen. Can you see this?
Yes.
Okay. Thank you. Selamat pagi. Assalamualaikum warahmatullahi wabarakatuh. Yang terhormat Bapak Trihandoko, Heru Triharjanto, Pak Farohaji, the organizing committee, distinguished audience. I would like to give talk a little bit about the aerodynamic design from a historical perspective, so from the past to present and to the future. Why have we gathered here today? One reason must have been that aviation has been growing in the past and also in decades to come. And we are all confronted by this fundamental question: can we follow this trend in a sustainable way? Can you see my my mouse, my cursor?
No.
No.
Oh yeah.
Okay.
Okay. It's visible.
Okay. Okay. I'm sorry that I had to apologize that I tried to share my face, but it doesn't work. So I apologize for that. So well, then this is the fundamental question that confronts us all. Can we follow this trend in a sustainable way? Well, in Europe, in answering this question, the Advisory Council for Aviation Research and Innovation has set goals in 10 themes, and these all must be achieved by 2050 and split over short, mid, and long terms. So the picture on the left that reflects how a common look of aircraft may change during this period. I'm not going to detail everything, but I will highlight goals and challenges most relevant with this talk only. So the first theme is that achieving climate neutral. So in the context of climate change, then by 2050, it must be achieved that net zero CO2 emission, 90% reduction of NOx, and 90% reduction of non-volatile particulate matters. And also in these goals, the citizen is at the center. So it has been set a goal that 90% of travelers of a door-to-door journey within Europe, it can be done in 4 hours. And there is also a 65 reduction of perceived noise. This is with a baseline in 2000. And then also Europe is concerned also about the competitiveness. So it means that things have to be done in a more efficient way, minimizing the cost. And not only 20 to 50% increase in fuel efficiency. It's not not only we have to show that the technology is able to do that, but also it has been implemented in most of the aircraft beyond 2035. So 75% of aircraft flying must have a reduction of fuel burn by 30 to 50%. And also very relevant to this talk is that research computing facility will no longer be a limiting issue. So high fidelity simulations using computational fluid dynamics and also a finite element method, they have to be possible. So these are all ambitious goals, but we are tackling it now. And how we tackle that? Well, we do collaboration at all levels. So departmental, institutional. So for instance, for departmental level in our department, we are from a department of flight physics and loads, about 16 people, and we are all specialists in our own field, consisting of mathematicians, engineers, and well, in aerodynamics, and also in loads and structural dynamics. So we collaborate, and institutional within NLR itself. NLR has 600 employees, and also with their own specialties in 3 divisions. I sit in the aerospace vehicle divisions, and we have a close collaboration also with other divisions, transportation divisions, and also a system division. And although the Netherlands is a small country, it is split into quite a few of regions, and within these regions, from north to south, from east to west, there are also collaborations going on. And on the national level, well, each country in Europe, they have their own national programs with national funding. And one of the most important thing is that in the international level, in the European Union level, we have been collaborating with in consortium consisting of partners from many countries, and it was started in 1984 by framework programs, and then continued in 2014 by Horizon 2020 program, and now what is going on is that Horizon Europe. And I should also mention successful programs in aerospace. It is a public-private partnership within the so-called Clean Sky 1 and 2 program. And what is going on right now is that the partnership within clean aviation, in which the public contribution through the European Commission amounts to 1.7 billion euros, and a private in kind from companies is 2.4 billion euros. So in all this collaboration, all forms of organizations can participate, like large industry, Airbus, Rolls-Royce, and other companies like also Leonardo helicopters, Airbus helicopters, and also a lot of small and medium enterprise can participate in here. And NLR is one of the research institutes in Europe, along with DLR from Germany, and also from, for instance, also from France, ONRA. So, and also a lot of research universities can participate in tens or maybe hundreds research projects. And the contribution, of course, can be distinguished into technological readiness levels. So from TRL 1 to 9, and each participants have different roles in this TRL. And in Clean Sky and Clean Aviation public-private partnership, we are looking into achieving TRL 6. So, and most of the projects started from TRL 3, and then at the end of project, TRL 6 are to be achieved. Now, I will show you some highlights from the projects. Of course, NLR is also involved in many projects, but what I'm going to highlight are 2 projects in which I have been involved personally and most recently. Well, actually, these 2 projects have been completed in the past 1 year. And I would like to focus on my specialty, that is aerodynamic design method. And it is good to show the historical and present perspectives for this method, which is important for achieving the goals that I showed you earlier. And it is also important that we cannot design if we cannot analyze. We should realize this. Which means that we can do any design exercise, but our design will be meaningful only if we can trust our analysis tool. And this is the reason that the NLR has invested in developing its own tool. So everything is within our control, and we have the specialist in the same room, and we have doing this for 30 years. And computational fluid dynamics method at NLR is an N-flow for a flow simulation and N-sense for a joint simulation. And it has been used for computational fluid dynamic, computational aeroacoustic, computational fluid mechanics, flight mechanics, and also aeroelasticity. So I would like to show a little bit about the historical perspective of the aeronautic design. Well, it started with an analytical method, an inverse method. So in inverse method, you want to realize a desired pressure distribution, let's say above over the surface of an airfoil. And this is a classical work of Lighthill in 1945. And also it was used still in 1990s to perform a multi-point inverse airfoil design method, and I will come back to that, what multi-point means. But this is in general it's no longer used, if not limited use, because of the analytical low fidelity approach. So it is only for potential flow, implicit flow. And hodograph method, it was pioneered also at NLR by work by Burstul in 1974, where you can produce a transonic shock-free airfoil design. But this is also a very limited now, the use of it, because the singular solution, so shock-free airfoil design, usually it is good only at one condition, but at other condition is very bad. And another category of method is numerical optimization, and this was probably pioneered by Higgs, is from NASA Ames and Henning, from McDonnell Douglas at the time, and still used in many variants and favors. So I would like to show you a little bit, because I'm going to dive in a little bit in this method, the gradient optimization algorithm. So consider here on the left is that on the vertical axis that's symbolizing aircraft drag, notated by P, and then drag is a function of flow variables Q, and also function of X. X symbolizes the aircraft geometry. So actually a design will happen from initial geometry, and then you want to optimize it as such that the aircraft drag will be reduced. And in doing so, we use the gradient information, so dpdx here, and that will guide us how to change the geometry in order to reach the optimum. So numerical optimization starting from initial x0 and then consecutively using iterative procedure approaching the optimal solution. And there three stages can be distinguished in this process: is analysis stage to determine P, geometry update stage to determine the modification of geometry, and a gradient stage to calculate the gradient. And in real life, well, actually, actually the aircraft in continuous domain, it is implicitly constrained by partial differential equation governing the flow in omega and bounded by the surface S. But in reality, we have to do that in a discrete domain, and there is a significant computational effort to determine P due to the procedure of solving the flow equations to get the flow variables. And then in the update states, well, in continuous domain, well, actually, X, it can be any point on S, is a factor of infinite dimension. And in discrete domain, then it is a factor of very large dimension, and it can be in the order of tens of thousands. And if you use that, the gradient is numerically noisy. Now I would like to tell you that in order to get a regular optimization, a regular behavior optimization, usually we do a parameterization to the shape. As such, the dimension is reduced, but still the dimension or the design variables is still in an order of 100. And by that, we can ensure a smooth, less noisy gradient and smooth surface. So a brute force classical approach, which is very expensive. This is usually we perturb each design variable, and then we do a flow analysis. And then this means that we would require n+1 solutions of the flow equations for each component of the gradient. This is prohibitively expensive. And especially if we consider that in the optimization, in real life situation, we have to deal with multidisciplinary situation, aeroelastic, aerothermal, air acoustics, and also multi-point. So if we consider the mission of the aircraft, we have to consider takeoff, climb, cruise, descent, and landing points. And then on the right, the statement of the optimization problem can get messy. So it consists of equality constraints, which is of flow nature and geometry nature, and non-equality constraints, and then the state constraint, the form of partial differential equations, and also boundary conditions. And also we have to deal with conditions which is not only steady, but it can be also periodic unsteady flow and non-periodic flow. An alternative is a joint method. I'm not going to go through these equations, but you can have an idea here that these methods can be mathematically intensive, but it pays off because you only need one solution of the flow equation in order to get and one solution of the joint solution to get the gradient. So it is independent of the number of design variables. Now I would like to give you a historical perspective of the joint method. Well, it started in 1970s, and in 1988, Jamieson's IK's NASA report that triggered worldwide interest, and also, of course, also at NLR, and I did my PhD on this topic. And also in NASA in 1997 and 1998, I visited there. And until now, it has been a workhorse for design in industries. For instance, you can see here in this project, this was concluded last year. And you can see on the left, this is a consortium, and it consists of industries, large industries, Airbus, and Dassault, and also Rolls-Royce, and then Research Institute, NLR, DLR, ONERA, and also universities and small companies. So a joint solution, a joint method has been useful, but from this project, then it is focused on multidisciplinary problems. And at NLR, we focused our effort in the design of a propeller. So you can, there are challenges by emerging concepts. So for instance, the Airbus racer concept, you can imagine there is a strong interaction of flow due to the presence of other components, overhead rotor, box wing, wingtip, and other propellers. Also in a distributed propulsion configuration like this NASA aircraft, there is also interaction between various components. And of course, nowadays, the urban air mobility vision triggers disruptive concepts. And this is aerodynamically, it is, if you want to optimize this configuration, it can be very complex because interaction from different propellers. And also, as in the goal that the citizen is center, as a central position, and we have to deal with noise and urban aircraft noise and also cabin noise. So this is results from our simulations to address these problems. Of course, we would like to reduce noise in our design. And we deal that by considering as isolated propeller and then tackle the aeroacoustic problem. So it is obvious that we have a need for an efficient and silent propeller. And this is a problem. We have to deal with the aerodynamics and acoustics in a simultaneous way. And we have to deal, on the left, you can see an unsteady problem. And well, the focus of development is that to develop an unsteady joint solver and also to make it affordable so that we can really design. And in the development, our approach is that we use a simple test case and then increasing in complexity from academic to industrial relevant configurations. You can see here it is from airfoil going to a simplification of one blade passage and then full three blade passage configuration. And first we have to make a reference solution. This is for a steady case, and then we have to verify the gradient and we have computed whether it is good or not, and we do that by making a comparison with the finite difference calculation. And then here we do another verification so that we can be sure that our gradient is good. And the second stage in this research is that we want to make it affordable by reducing requirements on the disk storage, I/O loads, and CPU time, by making in the unsteady case with inclined incoming flow that the reduction can be proportional to the number of blades. So this is an illustration on how we do that. We use the simplification of the NASA rotor as 67, and afterwards we deal with an industrially relevant propeller. And well, what you see here is that if we can deal only with one blade, then the requirement will be 3 times less. So this gives you an illustration how the domain looks like. So it's going like that. And then, of course, we have then to verify whether this reduction of the domain, it doesn't affect the accuracy of the gradient. Now, Also, this is I can say that this is a proof of concept for the new tool. That imagine that you have a fan, and in this case it is a 22 blade passages, and if you apply this method, there will be a 22 times reduction of the computational requirement. So instead of 22 hours, for example, you can do that within 1 hour. And this is the results, sample results of the tool. On the right, you see the performance map, so to speak, of the propeller, and where the efficiency has been increased tremendously. And also, what's significant here is that the stall of the propeller has been delayed significantly. In this problem, we use 369 design variables describing 9 airflow sections along the blade. And this is if you do that, if you deal with in an aeroacoustic manner, if you deal that in a steady manner or unsteady manner, you can see that the unsteady joint method, it pays off by giving a better solution. Now the second example is a next generation civil tilt rotor, which is also in a Clean Sky 2 joint undertaking framework. So we collaborate with Leonardo Helicopters, and so they have conceived this aircraft, and then the prototype of this will be flown maybe somewhere next year. And this is very relevant to the goal because it is a fast rotorcraft up to 500 kilometers per hour. This will contribute to the goal that within 4 hours travel journeys in Europe door to door can be made. And this is how we deal with that. The problem here is that if you see this configuration on this, you see this is an inlet to the engine, and this project is about distortion of the flow that is delivered to the engine. So what you see here is this is the inlet, and then here at the end is the entrance into the engine, and the flow quality must be of sufficient level so that the engine can perform very well. So Leonardo came with a baseline, and then we have to do a simulation, and the rotor is articulated. So beside the rotation, it also have pitch and flap motions, and there is also a global rotating domain of the rotor, which means that in an airplane mode, the position of the spinner is horizontal, and in the vertical takeoff and landing mode, it is vertical. And there are 15 load cases that we had to deal with, varying from airplane mode, transition mode, and fetal mode. And the objective is that in terms of mathematics, I'm not going to go through to these equations, but we need to reduce the distortion to the flow, and I will show you what it is. And it is also very important that any design, the formulation of the constraints, because the design have to be useful. So which means that we have to satisfy any constraints that has been imposed on our design. So this is an example that we have to modify the geometry with the constraint that the yellow area must not be penetrated. So this is a very stringent constraints that that we had to deal with, and only so actually we have a very small rooms to play. And this is the result of the optimization. I would like also to give you an illustration where in which that during the design process, a human insight is also very important. Here, actually, from this situation, what you see here is that the pattern of flow simulation, flow visualization, and this is a flow separation, and this has a high distortion, high flow distortion. And by human insight, if you see, we modified the geometry manually, and we can reduce the reduction by 73%. And then we went further by using an inverse by optimization, using the joint method, and we can reduce further the distortion by 37%. And this design has also been verified with in a large facility of the DNW wind tunnel. This is a full-scale test in terms of the engine intake, as such that you don't see here the rotor because it doesn't fit in the wind tunnel test section. And also part of the research is that before doing this, we quantify what is the impact if we do not include the rotor in the wind tunnel test. And so on the right, you see that a verification of the design that was done using CFD, and it is compared to the real flow situation in wind tunnel. And you see that the reduction in many cases, well, almost all cases have been realized and verified. And for case number 8, it is a special case for a very large side slip. So where the wind tunnel test, the blocking effect in the wind tunnel was too large, so that we don't have data for that. So in conclusions, I've shown you in a concise manner some sample or summary of research framework that has been done in our institute in the context of collaborations, and I've also shown the methods and projects, and these all contributing to achieving the goals in the context of both European Union and of course humanity, because it's really a concern of humanity, the climate change. And we have shown the potential of the research result in reducing the pollutant emissions by designing a more efficient propeller and also a more efficient engine, and also reduction of noise by designing a silent propeller. And also only by these 2 research projects, we can show that we can contribute to the goal of the journey duration within Europe. So where we can enable new concepts of multimodal transportation. And future perspectives, these are maybe immediate challenges in the future. Well, propeller noise can be distinguished into tonal, loading noise, and thickness noise. These types of noise are the ones that we have dealt with in the project that I showed you. And more challenging is the broadband noise, because we need an accurate determination of noise requiring turbulence resolving simulation. This is the time-consuming simulation along with near-field and far-field noise propagation methods, and also about the emergence of electrical propulsion. This may give us a higher degree of freedom in designing because we don't have to deal with compressor and turbine maps like in gas turbine propulsion. And of course, we can have a perspective of further collaboration, Indonesia and the Netherlands. And well, we have a history of long collaboration. One of the results is the wind tunnel at Serpong, which was commissioned in 1988. It was one of the results of our collaboration, where NLR took important role in this project. And also more recently, we have had collaboration with BPPT and also with LAPAN. And maybe as a final slide to tease you, we are also confronted by these disruptive concepts. There are hundreds of them in the world, people conceiving these concepts, and there are hundreds of startups. So we don't know if this concept will converge to one dominant design. So that one dominant design may be one that is conceived or developed in Indonesia. Thank you.
Okay. Thank you very much, Dr. Bambang. Maybe I will, if the participants don't know Dr. Bambang. Dr. Bambang is a senior research scientist at the Department of Flight Physics and Load, Aerospace Vehicle Division, Netherlands Aerospace Center, or NLR, and in Amsterdam. And he has a PhD degree in aerospace engineering from Delft University of Technology. And his research, as you can see from his presentation, is includes an unsteady aerodynamics, aerodynamic modeling, and for flight simulation. And he also involved in many projects, such as within EU framework programs such Horizon 2020, Clean Sky, Clean Aviation, as he mentioned in the his presentation. Now, ladies and gentlemen, thank you, Dr. Bambang, for your inspiring presentation. And we are moving to the last keynote speakers, that is Professor Kazuo Shiokawa. First, I would like to introduce Professor Shiokawa. He is currently professor and vice director at the Institute for Space, Earth, Environmental Research in Nagoya University. That is my alumni also. He's now the director of the Center for International Collaborative Research, CICR, of ISEE. And in 1990, he graduated from Tohoku, and then he joined Nagoya University, got PhD degree in 1994, and then become a visiting scientist of the Max Planck Institute in Germany. And he also a lot of projects. His topic of research in space science and aeronomy in general, particularly the dynamical coupling of the solar wind, magnetosphere, ionosphere, thermosphere, and mesosphere. So I will like to welcome Professor Shiokawa. Professor, the screen is yours. Thank you.
Thank you very much for your introduction. I'll share my screen. Can you see my slides?
Yes, sir.
Okay, so let's start my talk. Okay, as introduced, my name is Kazuo Shiokawa. I'm currently in the Institute of Space Environmental Research, IC, University, but I'm also the president of the Scientific Committee on Solar Terrestrial Physics, SCOSTEP. I'm very much glad to make this keynote talk with Professor Yukihiro Takahashi, because we were originally from same research group in Tohoku University in the same generation, with a supervisor of the Professor Hiroshi Fukunishi. And now we are in a different institution, but eventually we had a keynote talk in this same big conference. Okay, today I would like to address the outstanding topics on the predictability of the variable solar terrestrial coupling. Okay, this is a schematic movie showing the Sun-Earth relationship. The Sun emits both optical emissions and plasma particles, the latter called as solar wind, which sometimes causes big eruption as solar flare. The solar wind plasma hits the Earth. The Earth is protected by the magnetic field. The magnetic field forms the magnetosphere and tail-like shapes in the anti-Taiwan direction. When the tail is teared off, high-energy plasma is injected, and then the aurora appears, and also the that plasma affects the Earth's atmospheric environment. So the geospace around the Earth is dynamically changing because of the plasma and the magnetic field. This is actual observation of the solar wind plasma coming out from the sun. This is based on the SOHO coronagraph. This black object is a mask, and this white circle indicates the sun. And because sun is too bright, we put the metal mask in front of the camera to mask to avoid to prevent the solar emission and see only the solar atmosphere. And as you can see, the sun is emitting plasma continuously, and sometimes it makes a big eruption, and that hits the Earth. So in such a way, the Earth environment is strongly affected by solar plasma. And there are various phenomena in this Sun-Earth relationship, and this mechanism, the mechanism, not well understood. This is a summary figure of the outstanding challenging topics of the solar terrestrial coupling, mainly in their predictability. This is the sun, this is the Earth, and in between there are heliosphere, interplanetary field, magnetosphere, ionosphere, and the atmosphere. And the left side is the short-time variability, and the right side is the long-term variabilities. I will explain my presentation based on this view graph. For example, solar flare prediction is a big challenge, challenging topic. The flare, ultraviolet, and X-ray change ionization of the atmosphere and affect the atmospheric dynamics. And the solar energetic particles, SEP, is the other major particles and plasma from the sun, and also causes atmospheric composition change and such as ozone destruction. These solar energetic particles cause plasma damage to space and air vehicles and astronauts. So this is this shows the response of the atmosphere to the these various solar emissions, light emissions, the XUV, FUV, MUV, and depending on the wavelengths, the shorter wavelengths is absorbed in the higher altitude, and longer wavelengths can get into the lower atmosphere. So the distribution of the wavelengths causes the distribution of the altitude or the solar flare response of the atmosphere. The bottom panel shows the observed and modeled spectrum of the solar UV emission associated with the solar flare on January 2014. And you see there's some good modeling fitting to the observed solar spectra, solar UV spectra. So this distribution in the wavelengths causes altitude distribution of the response of the ionosphere to the solar flare. But this flare spectrum is different depending on the different solar flare. So prediction of the solar flare spectrum is very important to understand the response of the ionosphere to the solar flare. The right panel indicates one example of the response of the solar flare of the ionosphere. The top panel shows the GOES satellite solar X-ray flux, and at 17 UT, there's a strong enhancement of X-ray, which indicates the solar flare. And the second panel shows the geomagnetic field at Jicamarca in Peru. And as you see, the geomagnetic field response to in response to the solar flare, and that indicates the sudden enhancement of the electrojet current in the ionosphere. And also from the radar at Jicamarca, we can see the sudden decrease of the height altitude of the ionosphere. This is a velocity, downward velocity of the ionosphere, and because of the solar flare UV flux, the ionosphere is ionized and the height decreases in response to the solar flare. So in such a way, we can have a solar flare has causes significant effect in the equatorial ionosphere. Okay, in next, the sunspot evolution, solar flare, as I showed, which is challenging, and also the CME, coronal mass ejection prediction, and particularly the its direction of the magnetic field, IMBZ, interplanetary magnetic field, Z direction, is a big issue to accurate prediction of the geomagnetic storms. During the solar quiet time, co-rotational interaction region, CIR, also causes the geomagnetic storm, and its IMFBZ prediction is a challenging topic. I'll explain it here. In this panel, this is a view graph of the coronal mass ejection, CME. And in this schematic view graph, you can see the structure, expected structure of the CME, and in the front side, the magnetic field has a cloud-like shape associated with the CME. And this is the actual observation of this CME in the horizontal axis with the days, and 4 days. And this storm index indicates that the geomagnetic storm started at this point. And this is a magnetic field, particularly the red shows the magnetic field becomes southward, and the solar wind velocity increases and the density increases. So this is a big magnetic cloud hitting the Earth. And the important part is this IMF-BZ. When the BZ becomes negative, this, like this negative, this indicates the southward interplanetary magnetic field. And this southward magnetic field can interact with the northward geomagnetic field from the Earth. So then they can reconnect to each other, and they tear off the dayside magnetosphere and pushes the plasma into the night side tail. And then another reconnection occurs, and the plasma is injected to the Earth. So this BZ direction is an important part to whether it causes geomagnetic storm or not. If the even if the magnetic cloud hits the Earth, if the BZ is northward, this process does not happen. So we do not have a geomagnetic storm. So the BZ prediction is a really important but challenging topic, because the magnetic field prediction is very difficult, even in the modeling. This is the latest model of the solar wind plasma by the NDIL simulation. The center, this is the sun, and this yellow dot is the Earth. And this is the top view, and this is the side view from the sun to the Earth. So as you can see, we can simulate the plasma cloud hitting the Earth in this way. The sun is rotating with a 27 days period. So the things are rotating, and sometimes it hits the magnetic cloud hits the Earth. For this particular case, this is a recent one, and on November 25th, 3 days later, there's a small cloud hitting the Earth. So we have geometric disturbances on 3 days from today. And in the response in the Earth's magnetosphere, the storm substorm development and the consequent radiation belt development is very important. In the radiation belt development, plasma waves is an important essential role for the development of the radiation belt. So the coupling between the magnetosphere and the ionosphere is also essentially important for the global understanding of the ionosphere storm substorm disturbances. These phenomena cause precipitation of the high energy plasma into the ionosphere and atmosphere, causing dynamical variation and composition change. And plasma, this process also causes the plasma damage to the air and space vehicles and astronauts, and as well as the geometrically induced current, GIC. So I will explain these processes. The next figure. This is a figure of the dynamic variation of the radiation belt particles, electrons. The horizontal axis is 1.3 year from July 1990 to October 1991. This is one of the highest solar activity time in the 11-year solar cycle. And vertical axis is the distance from the Earth, is a unit of the Earth radius. So 2 is the 2 Earth radius, RE, 4 RE, 6 RE, and 8 RE. And the color scale indicates the about 500 to 600 kilo electron volt electron flux. That indicates the radiation belt electron flux. So you can see 2 high electron flux regions at around 2 RE and 4 to 6 RE. These are the inner radiation belt and outer radiation belt. Particularly the outer radiation belt, the particle flux changes significantly in response to the geometric storms. Because of the large geometric storm on March 24, 1991, the 2 inner and outer belt are connected each other. And this effect lasted very long time for several months or more than half years. And another storm happens like this. So as you see, the radiation belt electrons are dynamically changing associated with the geometric disturbances. And this dynamic variation of the radiation belt electrons are probably caused by interaction with the waves. As you can see in this movie, the waves, which have an oscillating electric field and magnetic field, can interact with electrons, which is caught by the geomagnetic field and make a cyclotron motion. When the cyclotron frequency is similar, comparable to the wave frequency, they can interact with each other, and eventually the wave can accelerate electrons to higher energies. Or of course, they can also decelerate the electrons to lower energies. But some of the selected electrons can form the radiation belt to very high energies, up to the mega electron volt. And there are 3 major waves that can interact with these electrons. One is the electron cyclotron wave, kilohertz wave, which is this one, which accelerates or loss of the electrons. The other is the electromagnetic ion cyclotron wave, which is the EMRC wave, which is a frequency about 1 hertz, which mainly causes loss of these electrons through the relativistic interaction between the waves and the particles. And finally, the last one is the PC5 waves with a frequency of the millihertz, which is about 5 minutes to 10 minutes. They also contribute to the acceleration and loss of electrons because this frequency is similar to, comparable to the rotation frequency of these electrons around the Earth. And the important point is that these wave part interactions are all on microscale phenomena. And it is really challenging to quantitatively estimate how these wave part interaction contribute to the global scale, global change of the radiation belt electrons. And as you know, these radiation belt electrons are dangerous for space, in space for human beings. They cause radiation damage to satellites and radiation dose for astronauts. And associated with recent solar activity increase, we started to see the geomagnetic storms in space around the Earth. In this February, we had a small geomagnetic storm happen as this shown in this storm DST index. This is horizontal axis is 1 month, and this is indicates the storm occurrence. And there's a small geomagnetic storm in early February in 3 to 5. And this storm causes the expansion of the upper atmosphere to higher altitude. And for the satellite, this means the atmospheric drag increases. And the satellites are decelerated. And as a consequence, up to the 40 Starlink satellite of SpaceX was getting lost into the Earth's atmosphere. So this is one example that as the human use of space is increasing, the effect of the short-term variability of the Earth space, geospace is very important for safe and stable use of the space by human beings. Now, from the Earth's atmosphere to this space, the gravity waves, tides, and planetary waves coming upward from the troposphere changes dynamic variations in the middle and upper atmosphere and ionosphere. These waves also trigger and control the plasma instability in the ionosphere, such as plasma bubbles, which cause interference of radio communication and GNSS positioning. However, prediction of the plasma bubbles, these instabilities are still under study, particularly for its day-to-day variability. This shows 630 nanometer air glow images obtained at SATA, Japan, showing a passage of the plasma bubbles. The 630 nanometer air glow indicates proportional to the ionospheric plasma density, and it can visualize the plasma structure in the ionosphere. And as you can see, the moving tree-like shape, dark area appears in the sky. This indicates the dark area, low density plasma in the ionosphere, which is drifting eastward, associated with the eastward plasma drift in the ionosphere. And this is called the plasma bubbles. And this plasma bubble occurs frequently in the equatorial ionosphere. Now, we know the mechanisms to cause the plasma bubbles, which is basically the Rayleigh-Taylor instability. I just explained this Rayleigh-Taylor instability. This is a schematic view of the ionosphere from south to the north. The magnetic field is perpendicular to this surface, and in the ionosphere, at the background, there's an eastward ionospheric current because of the gravitational force. And when the small dip is caused by gravity waves or some other disturbances, the ionospheric current cannot flow in this region. So you have a charge accumulation, positive and negative, and setting up the electric field, which is eastward. And by this eastward electric field and a northward magnetic field, the plasma start to move upward due to the E cross P drift. And that means the structure develops further upward and upward, setting up the instability station. So you cannot stop this upward motion in this situation. And even finally, it becomes like a tree-like shape plasma bubbles. So we can observe the plasma bubble in both northern and southern hemisphere simultaneously. This is an example when we observe the air glow plasma bubble in northern hemisphere Japan and southern hemisphere in Australia, Darwin, and simultaneously. And it's a symmetric structure, indicating that plasma bubble is developing at the geomagnetic equator and mapped to the northern and southern hemisphere along the geomagnetic field lines. And when we observe this plasma bubble in the sky, the radio wave of the GNSS satellite interfered significantly. This is one example obtained at Sumatra Island in Andhras University. We installed the GNSS receiver in the roof of the Andhras University building. And when this camera was installed in the Koto Taban in Sumatra Island in the EAR site in collaboration with ORPA-BRIN. And when we observed the plasma bubble in the sky, the GNSS satellite signal intensity significantly interfered. This is called scintillation. And eventually, we cannot use the GNSS car navigation system or satellite communication system. So the prediction of the plasma bubble is important for stable use of the navigation system and the communication between the satellite and the Earth. Now, the seasonal variation of the plasma bubble is well understood. We have a peak of the high occurrence in spring and autumn in the Asian sector. However, there is a significant day-to-day variability of the plasma bubble occurrence. This is a challenging phenomena for prediction of the plasma bubbles. This figure shows an example of the prediction from August 2013 to October 2013. The top panel two panels shows the GNSS signal and VHF satellite signal intensity, which indicates the occurrence of the plasma bubble as a S4 index. And when the S4 index is high, the plasma bubble is occurring. And the bottommost panel indicates the geomagnetic activity indicated by the KP index. And you can see when the KP index, which is the geomagnetic activity, is high, the plasma bubble is suppressed, disappears. So for this particular case, the geomagnetic activity suppress the plasma bubble and instabilities. This is a model result of the global GCM model result for the growth rate of the instability. And again, according to this geomagnetic activity, the growth rate decreases for these times. So this particular case, the day-to-day variability of the plasma bubble is caused by the geomagnetic activity. But it is still not well understood how these activities changes the plasma bubble occurrence, and the predictability is still challenging. So this is a summary view graph of the short-term variabilities of the space weather. The solar variability, solar wind, CIR, and coronal mass ejection, and UV radiation cause various effects on the human use of space, such as radio communication and GNSS positioning. And atmospheric wave from the lower atmosphere also contribute to cause the interference of the satellite ground communication through the initiation of the plasma instability in the ionosphere. And this storm effect also causes aurora and the high energy particle effects to the satellite and orbital change through the changing the atmospheric density. And finally, the electric current in the ionosphere can cause the geomagnetically induced current in the ground, and that affects to the power line transform. Now, let me move to the long-term variability. The solar dynamo evolution causes long-term variability of the solar total and spectral irradiance that causes thermospheric expansion or contraction, affecting the satellite orbit anomaly. This is a long-term variation that affects to the satellite orbit. However, these solar total and spectral irradiance variations are still not well understood. Recent studies also suggest that solar cycle variability can be predicted by using the actual dipole moment of the sun for the next 5 years. This solar cycle variability can cause modulation of the cosmic ray and solar and magnetic plasma. And that results in the composition and dynamical change of the atmosphere. And that also in the long term, that may affect to the Earth's climate change. And together with this so-called anthropogenic effect, greenhouse gas effect, the solar variability may cause the climate change. However, the prediction of the solar cycle variability for more than 5 years is still a challenging topic. So this is the view graph of the sunspot number, not the COVID-19. This is a sunspot number graph, and for the recent 17 years. As you may see, solar activity has 11-year cycle. Now we just passed through the solar minimum in 2020, and in getting into the active time, and the solar activity is rapidly increasing. Now, this is the prediction of the maximum sunspot number for the next cycle 25 by using various different prediction schemes. And as you see, some scheme predict the next solar maximum is very small, which is 50. And another scheme indicates that next solar maximum is very active, like more than sunspot number of more than 200. So this still indicates our current knowledge diverges from minimum to very small to very large for the next 5-year prediction. And we are trying to understand the processes to make more accurate prediction for the sunspot activities. And anyway, the sunspot solar activity is increasing now, and we are starting to have its consequences on us, as I showed before, as a Starlink satellite effect. And this is an example of the possible solar variability effect on climate change. This horizontal axis is 400 years from 1600 to 2000, and the top panel shows the sunspot number. And the solar activity has an 11-year cycle, but you see it has a longer time scale variations like this. And the solar activity and the solar total irradiance varies in the second panel. This is the solar total irradiance varies associated with this long-term solar variability. And when the solar activity is small, the solar total irradiance becomes small. And this is a magic number of the solar total irradiance, which is about 1,360 watt per square meter. This is a solar emission in the visible wavelengths. And the variation associated with solar activity is only 0.1% in the solar total irradiance. And in the bottom panel, they compare the temperature of the Earth with the solar total irradiance. And you can see there's a clear correlation between the temperature of the Earth and the solar total irradiance. And the recent 50 years, we have a sudden enhancement of the temperature. This is clearly not the effect of the solar total irradiance, but because of the greenhouse gas effect. But before that, there's a good correlation between the solar total irradiance and temperature. And this good correlation cannot be explained by this 0.1% solar total variation. So we need to think about some other additional effect to cause this good correlation between the solar activity and the surface temperature. This indicates the several models. First of all, we should understand what causes this 400-year variability, and that is we need a precise modeling of the solar dynamo effect in the inside of the sun, solar interior. That is one big challenging topic, to understand this solar variability. And for the effect to the Earth's atmosphere, there are several ideas, models to explain these variations. One is that the solar total irradiance causes the change of the sea surface temperature, and this sea surface temperature change affects to the climate. The other is solar UV emission. Also, the total solar radiance in the visible wavelengths is only 0.1%, but UV emission can change about 6 to 8%. So this big amplitude of solar UV emission can change the ozone temperature through the temperature ozone absorption that changes the temperature in the middle atmosphere. And through the dynamic coupling between the middle atmosphere to lower atmosphere, this big temperature change may cause the climate change on the surface. The other model is that plasma from the space that causes aurora, but also causes ozone destruction, and through the Hawks and NOx generation, and that also changes the temperature in the middle atmosphere, and again the dynamical coupling changes the climate on the Earth. So, but all these are just ideas and do not quantitatively evaluated. So this is this quantitative assessment of these ideas is still a challenging topic. This shows the latest result of the solar UV measurement. This is a horizontal axis is a wavelength in the angstrom, in nanometer, and this indicates the TC1 measurement of the solar total irradiance, including the UV visible to infrared range, and they made a very high resolution measurement of the solar total irradiance. So this kind of effort to measure the total solar irradiance is now continued on by the satellites. And for the plasma precipitation, when the high energy particles, plasma sheet particles with the kilo electron volt precipitate to the ionosphere, that causes aurora. And it also causes NOx generation. And this NOx causes destruction of the ozone and affects the middle atmosphere. And the radiation belt particles, which has the energy of the mega electron volt, which directly cause the destruction of the ozone in the middle atmosphere. The right panel shows the one of the superposed epoch analysis for the response of the middle atmospheric ozone to the geomagnetic storm. This horizontal axis is the days from the start of the geomagnetic storm, and this vertical axis is the altitude, and the color scale indicates the ozone amount. And after the geomagnetic storm started, then the ozone in the 70 to 75 kilometers clearly decreased about 20 to 30%. So this clearly indicates that the radiation volt electron precipitation impacts the atmospheric ozone decrease, and that may cause the that will cause the temperature variation in the middle atmosphere that may affect to the climate change for long term. But it's still challenging to understand how the long-term effect of this ozone change. Now, finally, I would like to introduce the SCOSTEP activities to understand these challenging topics. The SCOSTEP, the Scientific Committee on Solar Terrestrial Physics, is one of the thematic organizations of the International Science Council. And SCOSTEP runs long-term 4 to 5 years international interdisciplinary scientific programs of the solar terrestrial physics. The science, capacity building, and outreach are the three major tasks, activities of the SCOSTEP. These are the 4 to 5 year programs operated by SCOSTEP. Recent programs is causes to which is a climate and weather of the Sun system. That means the short-term space weather and long-term space climate in the Sun system. And recent one is a VERSITY, which focuses on the decreasing trend of the solar activity, so the variability of the Sun and its terrestrial impact in 2014 to 2018. And currently, the SCOSTEP is running the PRESTO, predictability of the variable solar terrestrial coupling. As I showed in this talk, the predictability is essentially important for the application, understanding of the space effect to the human use of space. The mission of the PRESTO is to identify the predictability of the variable solar terrestrial coupling performance metrics through modeling, measurements, and data analysis, and to strengthen the communication between the scientists and the users. The PRESTO has 3 pillars: some interplanetary space and geospace, and the pillar 2, space weather and the Earth atmosphere, and pillar 3, solar activity and its influence on the climate and the Earth system. And for further communication of PRESTO activity, we share the information through the SCOSTEP all mailing list. So if you are interested in subscribing this mailing list, please send email to SCOSTEP request at bc.edu. Or you can visit also the SCOSTEP website. Here is the chair and co-chairs and co-leaders of the 3 pillars of the PRESTO, who are distinguished active scientists from various countries. Under these 3 pillars, several major scientific questions have been addressed, and scientific working groups are working to challenge these scientific questions. SCOSTEP used to support more than 10 workshops and symposiums per year for its program. However, because of the COVID-19, a face-to-face meeting becomes difficult. So PRESTO program has started online seminar series. So far, we have organized 15 online seminars by distinguished scientists related to the PRESTO program. This is we have 5 online seminars in 2022. And PRESTO also distribute newsletters every 3 months, which contains articles on the latest PRESTO-related activities, highlight of young scientists, meeting reports, and short news. This newsletter is distributed through the SCOSTEP all mailing lists. And SCOSTEP PRESTO has a funding, financial support for organizing international campaigns and meetings and database construction every year. And SCOSTEP also supports the financial support for capacity building activities such as schools, of the organizing schools for solar terrestrial physics. We just announced the opportunity for 2023 with a deadline of January 10th of 2023. So if you are interested, please visit our site, this one, in the SCOSTEP website. SCOSTEP also organizes the online capacity building lectures to provide high-level lectures to the students and early career scientists. So far, we have organized 15 lectures. This is a lecture in 2022. And SCOSTEP also supports the capacity building activities. In 2022, we supported capacity building schools in Spain, Bulgaria, Cote d'Ivoire, and Argentina. Yeah. We also supported the schools in Indonesia, like this in 2020, 2012, 2015, and 2018. So if you are interested in organizing a school, please visit the SCOSTEP site. As a capacity building activity, SCOSTEP also distribute science comic books to introduce topics of the solar terrestrial physics to the public, particularly to the kids. These comics books were originally written by Hayanon in Seibundo Shinkosha in collaboration with Professor Yosuke Kamide and in support with the SCOSTEP courses program. Since then, they have been translated into English, French, and some translation is also going on Czech, German, Korean, Tamil, Hindi, Italian, Japanese, Urdu, Russian, and Spanish. This translation activity is still going on by volunteer scientists in several countries. So this is all my presentation. As a summary, I again show this figure and the challenge of the challenging topic in the solar terrestrial coupling. there are various challenging scientific topics in solar terrestrial coupling system. Study of all these topics contributes safe and stable use of space by human beings, as well as our understanding of space effect on Earth's climate change. For those who are interested in the SCOSTEP activities, please visit SCOSTEP website. That's all. Thank you very much.
Thank you very much, Shiokawa Sensei. Ladies and gentlemen, now we have question and answer sessions. So we invite the participants to write some questions in the chat, and if we cannot answer it during the session, I hope both Sensei, Takahashi Sensei and Shiokawa Sensei and Dr. Bambang will answer it privately via email. Okay. Now I think there are 3 questions that I have received. The first one is to Professor Takahashi from Laras Moyo. He is from Rocket Technology Center. He has animated weather visualization from microsat sensors is very informative indeed. But is it already applied to the airlines industries? Or did the airlines have a faster solution? How fast microsat images can be constructed in 3D model? Thank you. That's the question. I think there are 3 questions for, please, Takahashi Sensei to answer it.
Yes. So actually, we carried out the airplane measurement for 3D stereo imaging already, and flying over the typhoon ice, and it was greatly successful. But using the aircraft is not so easy because some regulations to install the instrument is very strict. So therefore, it takes too much time to organize the aircraft measurement generally. It's possible for campaign base, but if we want to use the commercial airlines, so it takes too much time and too much effort. So therefore, and another aspect is the coverage of the aircraft. Aircraft covers not so huge areas, and especially over the ocean. So we want to know the development of the typhoons in the middle of the ocean. So it's not easy to organize prepare the aircraft to flying over such area. So on the other hand, the satellite can watch anywhere immediately, but once or twice a day. So Indonesia has Lapan satellites already. So you can operate the satellite to watch a specific area 2 times daytime and 2 times nighttime generally. So then the cost of the unit area, for example, 1 hectare data is much cheaper than airplane or drones. So therefore, we should think about the combination of the aircraft measurement and satellite measurement. Is that the answer for you? Any more questions? I'm sorry.
I think how fast the microsat images can be constructed into 3D model. I think that his last question, because the first one, the first and second one related to the airlines. Okay.
So at this moment, the reconstruction of 3D using the several pictures taken by satellite takes too much time. So therefore, it's a kind of exercise phase. But in the near future, so if we can own and operate the several satellites in space, then we can download the data immediately after the capturing. So our target must be order of 10 minutes to 1 hour in the future. for the thunderstorms, that should be less than 10 minutes. It's a kind of challenge, but for the typhoons, so the once a day is still useful for the predicting the next day activities of typhoons.
Okay, I think it's enough. The answer, thank you, Professor Takahashi. Maybe let's move on to the question. The second question is coming from Muhammad Ilham Adinugraha. He's from National Agency for Research and Innovation. He asks that you mentioned during your presentation about the opportunity of small, medium enterprises can contribute to aerospace research, in what capacity they can contribute, and how exactly it works. This is for Dr. Bambang Sumarwanto. Please, sir, to answer this one.
Ya, terima kasih Bu Lilis. Yes, to Pak Muhammad Ilham, thank you for your question. Well, it's actually there are diverse types of small and medium enterprises. In the example that I showed, well, actually, how they got on board. Every research project started with a proposal, and then during the proposal preparation, then we are looking for partners, and then well, then partners know what is the scope of the project, on what will be done in the project, and what is the goal of the project, and then they can propose their contribution, and if that fits in the project, then they can get on board. And in the example that I showed, for instance, the small medium enterprise is actually an engineering bureau. So, but they develop their own software, and this software is applied to the test cases, for instance, that is provided by the large industries like Airbus, like Rolls-Royce. So in the end, well, it's a win-win collaboration. So they well, after the project, then they can exploit the results to provide services not only for the industry that was involved in the project, but also for other industries. And in other projects also, well, a small company like less than 50 people, they build propellers, rotors, and composite materials and other components of the aircraft. So they develop the method of manufacturing and, well, that sort of things. I hope that answered your question.
Okay, thank you, Dr. Bambang, for the answer. And the last question is for Dr. Professor Shiokawa. This one is also from Muhammad Ilham Adinugraha from BRIN, and he asked that, is there initial hypothesis that explaining why geomagnetic activities could suppress the plasma bubbles or affect the variability of the bubbles? Please, sir, Sensei. Mr. Wahyudi, please unmute Professor Shiokawa, please.
Thank you. Okay, now I can speak. So, well, one idea is that when you have geomagnetic disturbances, that energy goes to high latitude, and high latitude atmosphere is heated, and from the heated high latitude atmosphere, there's a wind is generated to the equator, and the equatorward wind, southward wind in the northern hemisphere, equatorward wind turns to the westward wind because of the Coriolis force. So during the geomagnetic storms, you tend to have westward wind at the middle and low latitude, and that westward wind suppress the eastward plasma motion and eastward electric field. Eastward electric field, and that causes generally the downward motion of the in the plasma bubble is generated in the sunset terminator because of the sudden ionospheric height increase. But if there is a westward wind, prevailing westward wind, that upward motion of the ionosphere is suppressed. So that is probably the mechanisms to suppress the plasma bubble generation by the geomagnetic disturbances through the neutral wind from the high latitude to low latitude.
Okay, I think that's will answer, will satisfy the question. And is there any question? I invite the participants to write their questions in the box, the chat. Okay, if there is no question, I think I have my own question. Is it okay? For example, for Professor Shiokawa, you mentioned about geomagnetic storm, right? Does this storm will affect the magnetic field of the Earth, and will these changes of the Earth magnetic field will affect the living creatures, for example, the animals, because I have read somewhere that they also use the Earth magnetic field for navigation and something like that. Please, that's it. I think
it's still on research. There's some report that during the geomagnetic storm, some animals fails of direction, like fish, like whale, or like long distance traveling bird may fail their direction because of the geomagnetic field variation. But actually, during the geomagnetic storm, the variation of the geomagnetic field is only 1% or less than 1% from the background field. So I'm not sure whether that animals are feeling that small change of the geomagnetic field during the storm. But there's some report that the birds or whales fails their direction during the geomagnetic storm.
Okay, thank you very much. And I think we still have time for, okay.
May I have one more note?
Okay, sure.
Yeah, sorry, I should mention about the SCOSTEP, one more support for SCOSTEP. SCOSTEP recently announced the opportunity for students as a visiting scholarship. The students who are interested to visit foreign countries, established high-level institutions, we can support their travel and staying for 3 months in that high-level institutions. That is called the SCOSTEP Visiting Scholar Program. So if you are interested, the students, if you are interested in visiting, using that scholarship, please visit our SCOSTEP site. That's for only for students.
Okay. Oh, not for researchers, sir.
Yeah, for research, yes.
Okay, so I encourage the students and the researcher to open the SCOSTEP's website and see if they something they feel interested to join. Okay, and there's one more question from me to Dr. Bambang Sumarwoto, because you mentioned about the private-public partnership. I want to, from your observation, I want to know what is how to make the public partnership be successful during your observation from the European collaborations. If you don't mind to answer it, sir. Pak Wahyudi, di unmute Dr. Bambangnya. Mr. Wahyudi, I hope you can unmute.
Yes, I think I'm unmuted now. Can you hear me?
Yes.
Yes. Well, it is. Well, of course, I'm not. I wasn't involved in how, for instance, Clean Sky framework has been initiated, but there was a public event that I attended 2 years ago, and it needed a long preparation and also a long negotiation between the public partner and in this case the public partner is the European Commission. And well, actually this is an entity who distributed the taxpayers' money, and the private partner are the industries. So it is a long interaction between them, and then deciding what are the contributions in what form. And well, it's actually what happened in this partnership is that very good ones are that the industrial partner, the private partners, they provide industrial problems, and these industrial problems stimulate the stakeholders to innovate. So innovation, it must really result in innovation. And I showed you the focus was from TRL 3 towards TRL 6. So it has been going very efficiently and very effectively, and where any organization in Europe can participate with their own capacity and their own knowledge and capability. And of course, in this case, the industries involved will be the main users of the results of the projects. But because the results are also available in public, and these partners are also free to provide, let's say, services or knowledge to other industries. So in the end, it benefits well all the communities. I think that I hope that answered your question.
Thank you very much. Because we are trying to encourage public-private partnership here in Indonesia. So, and my last question is to Professor Takahashi. You mentioned about the multi-point imaging, right? The method, is it already applied to any satellite now? I think I got because the connection is not so good, so maybe I missed it. Okay.
I'm sorry. So we did with our micro satellite developed together with the Philippines. So,
Okay.
but this imaging is not so special. The BRIN satellite can make it. So therefore, just watching a certain place and flying over like this. So it's quite easy, and just 10 seconds measurement can make the 3D of the clouds. So then if we Japan, Indonesia, and the Philippines work together, then the observation frequency may be improved significantly. So then we can monitor the development of the typhoons. So this is one possibility. So, and we want to suggest also the private sector activities for the satellite operations. So if the private sectors can participate in the building or operating the satellite, then they can earn the money from the management of the agricultural farms. So, or the proposing the alert to the extreme weathers. So probably the meteorological agency or meteorological companies may be interested in that. So therefore, but the important thing is the collaboration under the international communities. So the one country launched the 3 satellites, and the 10 countries, then 30 satellites can be used. And our satellite can fly over Indonesia, and your satellite can fly over Japan. So then vice versa. So then we can increase the number of the satellites very easily under the international cooperation. So this is my suggestion. So then we want to discuss this matter with the BRIN and the Indonesian government if possible.
Okay. Okay. Thank you very much. I think Dr. Heru will follow up. Okay. Okay. If there any questions? If there's no question, I think we will end our question and answer session. And I will thank you. One more. Oh, okay. Okay. After the discussion, after this one, I think. Okay. I will say thank you for joining us today, and I apologize for a little bit delay because the communication problem and also the hardware problem. Actually, we practiced yesterday, there is no problem, but today there's some problem. Okay, apologize that, and thank you very much, Professor Takahashi, Professor Shiokawa, and Dr. Bangbang for taking your time to give us very inspiring and comprehensive lectures that I think that stresses the point of internal collaboration, right? The need for international cooperation so that we can promote and or enhance the life of the mankind here on Earth. And I think from Takahashi mentioned that the advancement of the component and also the methods for the satellite that can be utilized to improve the life of humankind on Earth, and also the lecture from Dr. Bangbang stresses about the importance of the collaboration within a nation in the region, and also some topics, interesting topic in the aerodynamics that can solve also the problems to promote the lower the emission and also lower the journey time and so on. And Professor Shiokawa also mentioned about the interesting topic regarding the solar terrestrial phenomena, right? And also either in the short-term reliability or long-term reliability, how we need to understand those phenomena to enhance also our human life here on Earth, so we can understand to improve the communication, also improve how to understand climate change and so on. And I think that's all my conclusion. And thank you so much once again to all the 3 keynote speakers, and thank you so much for the participants and also distinguished guests that are present in this Zoom. And I wish you a very wonderful day and hope we can meet again in other occasion. Thank you. And I give it back the screen time to the Faisa. Thank you very much. Have a nice day.
Thank you.
Okay, thank you, Mrs. Lilis, for leading the keynote session. Ladies and gentlemen, that was our keynote speech session. Before moving to the next agenda, we will have photo session first. Please make sure that your Zoom video is on now. Okay, so dear host, you can take the screenshot now, please. Okay, please wait a minute. So we have 6 slides of participants. Is it finished? Not yet.
Okay, Mbak Faisa, let's
Okay.
continue.
Okay, thank you. So, Excellencies, participants, ladies and gentlemen, there will be break time for pray and lunch until 12:50 and followed by parallel seminar session. For parallel session will be shared in breakout room. Please join your room according to the schedule given, and please make sure your Zoom name is in accordance with the instruction. We will meet again in this main room for closing today's agenda. Please leave the breakout room to join the main room just after all presentation in your room is over. Good luck for your presentation and see you.
Thank you.
Thank you.
you.